Welcome to The Explainer. Today, we're diving deep into one of the biggest, most intricate challenges in all of modern robotics, building a hand that has the same dexterity, the same delicate touch as a human.
I mean, why is it so hard for a robot to do something simple, like handle an egg or fold laundry with the same skill we do? It seems so easy, right? We do it without even thinking. But for a machine, that's a monumental task. And the answer goes way, way beyond just copying our movements. It's about a fundamental shift in thinking. So let's get into it.
You know, for decades, the whole goal was something called kinematic replication, which is just a fancy way of saying, let's make the robot's joints bend like ours. But that approach kind of hit a wall. The new frontier, the thing everyone's focused on now, is embodied intelligence. The big idea here is that a truly dexterous hand can't just be a mechanical puppet. It has to be an integrated system, one that can feel, adapt, and actually learn from its environment.
All right, so here's how we're going to break this down. We're going to look at this challenge layer by layer. First up, the nuts and bolts, the physical hardware. Then we'll get into the sensory world, how a robot feels. And finally, we'll see how AI pulls it all together to create this incredible new form of intelligence. So let's start with that foundation. I mean, before a robot can think, it has to be able to act, right? And that all comes down to building the muscles and nerves, solving the really tough problems of mechanics and sensors right from the get-go. Okay, let's dive into that first layer, the mechanical hardware. This is the absolute bedrock. Think about it. The motors, the gears, these are literally the muscles and joints of the robot hand. And their performance, well, that sets the absolute hard limit for what that hand can ever hope to do. One of the biggest enemies in this mechanical battle is something called backlash. It's this tiny, almost invisible gap between gear teeth. It sounds like no big deal, right? Wrong. In robotics, it's a precision killer. A tiny bit of wiggle in a gear becomes a huge problem by the time you get to the fingertip. And here's what that looks like in the real world. An error of just half a degree. I mean, that's minuscule. Can make the robot's fingertip miss its target by almost 9 millimeters. That is the difference between gently picking up a glass and just knocking it right off the table. And that is why this one little component, a precision reducer, is so incredibly critical. Now, when it comes to these super specialized components, one company has basically cornered the market, Japan's Harmonic Drive Systems, or HDS. They control something like 70% of the entire global market. And while that's a testament to their amazing technology, it's also created this massive supply chain bottleneck for the entire robotics industry. But, a bottleneck like that is also a massive opportunity. And because HDS has had such a lock on the market, it's kicked off this race. We're seeing new players from Japan, China, and Korea jumping in, and they're ramping up production like crazy. They're all trying to meet the insane demand from the cobot market, these collaborative robots, which all depend on these super precise parts. For a really high-profile example of this, just look at Tesla's Optimus humanoid robot. This is the perfect case study. They're trying to solve this exact mechanical challenge, pushing the absolute limits by designing and building all these complex systems from the ground up. And what's so interesting about Optimus is that it perfectly illustrates the core engineering trade-off here. They've tested a bunch of different approaches. One is using these ball screw systems, which give you super precise control right there at the joint. Another way is to use tendon systems, kind of like our own bodies, where the motors, the muscles, are actually in the forearm. That makes the hand way lighter and less complex. But the fundamental challenge is always the same. How in the world do you cram all that power and precision into a human-sized package? Okay, so let's say you've done it. You've built a mechanically perfect hand. Guess what? It's still not enough. It's like having a world-class athlete who is blindfolded and wearing thick gloves. They can't feel a thing. So the next huge leap we have to make is bridging this sensory gap. And this is the really crucial point. Without a sense of touch, a robot is basically flying blind. It's working with incomplete data. It only knows where its joints are supposed to be, not what's actually happening when it touches something. It can't feel an object slipping. It can't tell if it's applying too much force. It's just guessing. But there's been a major breakthrough that might just be pointing the way forward. Researchers in Beijing have developed something they're calling the F-TAC Hand. And really, it's a massive leap in giving robots a human-like sense of touch.
I mean, just look at these numbers. They've covered over 70% of the hand's surface with high-resolution sensors. And the density of these little sensor points, they call them taxels, is getting close to human levels. This isn't just a small step. It completely transforms the hand from a dumb tool into an active, perceptive system. It can actually feel the shape and texture of things. And the results? Well, they're pretty stunning. Get this, when they had the robot do complex tasks, like manipulating a few objects at once, the success rate without touch was just over 50-50, basically a coin flip. But with touch, a perfect 100% success rate. That right there proves it. Touch isn't just a nice-to-have feature. It's absolutely fundamental. It is a requirement for real dexterity. Okay, so we've got the muscles, the mechanics, and we've got the nerves, the senses. That brings us to the final piece of the puzzle, and maybe the hardest one of all, the brain. How do you actually control this incredibly sophisticated piece of hardware and make sense of all that data flooding in from the sensors? Well, this is where you run smack into something called the embodiment gap. And it's a huge problem. See, you can't just record a human's hand movements and play them back on a robot. Our hands are made of bone and muscle. The robot's is made of metal and motors. They're just different. A simple copy and paste approach is doomed to fail. So the real solution, the big unlock, isn't to copy the movement. It's to translate the intent. You have to figure out what the human is trying to do. And for that, you need a really smart AI to act as a sort of intent translator. So how does this AI translator actually work? Well, first, it just watches a person perform a task. But here's the clever part. It's not just tracking joint angles. It's analyzing the relationship between the hand and the object to figure out the goal. Is the person trying to lift that bottle, or are they trying to unscrew the cap? Once the AI understands the why, the objective, it then figures out the best way for the robot's body to achieve that same goal. It creates a totally unique plan, custom-tailored for the robot. So, if there's one thing to take away from all this, it's that the quest for the perfect robot hand isn't about finding a single silver bullet. The future isn't just about building a better motor, or a more sensitive sensor, or a smarter AI. The real breakthrough, the future, is all about the integration, how you seamlessly weave all three of those layers together. So, we've gone on this journey, right? We started with the mechanical foundation, where things like precision gears set the absolute physical limits of what's possible. Then we saw how sensory perception, especially touch, is totally non-negotiable for adapting to the real world. And finally, we saw how AI acts as that crucial translator, bridging the gap between what a human wants to do and what a robot can physically do. And that really brings us full circle, back to that paradigm shift we talked about at the start. The future of the robot hand isn't defined by how it moves, but by what it feels and how it learns. We're moving away from robots as dumb puppets that just follow commands and toward truly intelligent partners that can perceive, understand, and learn on their own. Which leaves us with a pretty big question, right? When robot hands can finally feel, adapt, and learn just like ours, what tasks are really left only for humans? It's a question that really makes you think, and based on the incredible progress we're seeing, we're probably going to find out the answer a lot sooner than we expect. Thanks for watching The Explainer.